Okay, so what we're going to talk about here is kind of tied into what we've been doing with the waves, the frequency and the wavelength and the energy that we all did at the beginning of this chapter. Okay, and it's kind of tying into this very theoretical concept, which is referred to as the quantum mechanical model of the atom. Very, very theoretical, very hard for us to kind of wrap our head around. But I'm going to try and make it as reasonable as possible. So, if you've ever made toast, you take a piece of bread, you put it in your little toaster, and you may notice that the filaments, the little pieces of metal inside the toaster, start to glow red. Well, you're adding electricity, and they're glowing red. And so what you're getting is you're getting light, and light is a form of electromagnetic energy. And it's just visible light. So if you're looking at your oven, you turn on your oven, you flip on a switch on your nightstand, light, or whatever, you see an incandescent light bulb or a fluorescent light bulb like we have in here, what happens is they generate heat, okay, that's infrared radiation, remember where that is on the spectrum, and light, which is in the visible part of the spectrum. And what they do is they add energy to the elements, and they start to glow. Fluorescent bulbs work similarly. You add electricity, but they run an electric current through a gas, and again, it starts to glow, kind of more like a neon light. If you've ever seen like an open sign or whatever in a store, that kind of an idea. So when you add energy to atoms, you give them electricity, they give off light. But we're going to talk about how that happens, and it's a little bit strange. So if you add energy to the elements, they are going to emit energy in the form of some kind of electromagnetic radiation. So visible light is part of that spectrum. But so is radio waves and infrared, which is heat, and ultraviolet. They're all different forms of energy. But the thing is, when you do it just to elements, individual elements, you don't get a rainbow. Okay, rainbows are what you see, they're called a continuous spectrum. In other words, there's no breaks in it. It's, Roy G. Biv, and it just kind of blends from one to the other. In elements, what you get is what's called a line spectrum. And this is what it looks like if you look at it through a spectroscope. If you took physical science in 9th grade, you probably did these kinds of things, the little scopes you look through, and you see these things, these lines. So it's not a complete rainbow. Hydrogen is completely missing yellow. Okay? Helium's completely missing green. So is lithium. So it's not a continuous spectrum. We don't have all the colors of the rainbow. And so we're trying to explain this. And the way it works is we refer to the atom as being quantized. And that's a fancy word that basically means it only is allowed, okay, based on experimentation, allowed, we have observed, that it can absorb and emit specific amounts of energy. It's quantized, meaning that you're only allowed certain amounts. And so as a result, atoms give off only certain frequencies. And again, remember, frequencies are related to energy. Okay, so certain frequencies result in certain energy. So the energy that they give off, the light they give off, has certain frequencies, and as a result, certain wavelengths. So this is kind of what they're trying to say. They're trying to say that this is a continuous spectrum. In other words, the amount of energy increases, and every energy wavelength or frequency is represented. But in an atom, like hydrogen, there's only certain energies. And each one of those four, this one is red. This one's kind of a, I think it was kind of a blue-green color. This is a blue color. And this is a purple, violet. And so each one of these lines that we saw corresponds to a certain color, and since it corresponds to a certain color, it corresponds to a certain frequency and a certain energy. So it's kind of backwards logic when they're doing this. It is very difficult to understand because in the real world, we don't have situations like this. Okay, what is probably happening is that the atom, so let's say this is hydrogen, it's got one little proton in the middle, it's got one little electron on the outside, and the electron is zipping around, and you remember your Bohr model of the atom. Okay, we were talking about that with the Rutherford model of the atom, where the electrons are traveling outside the nucleus, and it tries to get as close as possible to the nucleus, but doesn't collapse because it's not allowed to. This is referred to as the ground state, okay, meaning it's at the lowest possible energy, it's very stable, it enjoys being there, so to speak. If I zap it with some electricity, what happens is the electron that's there will jump up to what's called a higher energy level. It'll jump further away from the nucleus. And that's referred to as an excited state. It has a little bit more energy because it took in that energy from the electricity. Okay, so I gave it a certain frequency, and that wave pushed that electron up to a higher energy level, but it doesn't stay there very long. And it wants to drop back down to the ground state. That's the term they use. So here's the electron. I zap it with electricity. So I add electricity to it. And then when it drops back down, it gives off light. And that light has a certain frequency. And as a result, it has a certain energy. And so we can say that the electron is only allowed to give off that much energy when it drops. That's what the quantized means. So when the electron drops down to the ground state, the energy that it took in from electricity is given off in the form of light. And generally speaking, we're dealing only with visible spectrum, but it falls anywhere along the spectrum. Anywhere. It's just a matter of how far it drops, how much energy it has. And because it's only allowed to jump from one energy level to the next, they're going to be the areas. They're only allowed to have certain frequencies when they drop back down. It's not like they can get off in the middle. The way I like to use an analogy is it's like taking an elevator inside a hotel. Okay, so you're on the ground floor, right? And say you're staying on the third floor. All right, you add electricity and you move up to the third floor. You can't get off in between because your room is on the third floor. You can't get off at floor 2.15 or floor 1.5. You have to get off at whole number areas. And when you drop back down to the ground state, you don't get off at floor 1.3 and then walk the rest of the way down or anything. You go literally transition between energy levels. So it's like floors in a hotel being in an elevator. However, when we're talking just one electron, we can't see it. And that's referred to as a photon of light, that light that comes off. But when you have billions and billions of them, okay, what you end up getting is you get the red line. You end up getting that teal color line, a blue, and a purple. And those tell us this is the energy for the first drop for hydrogen. So the first floor to the ground floor. This is the second floor to the ground floor. And this is the third floor to the ground floor and the fourth floor to the ground floor. And so it's a transition of elements or electrons within the element between the energy levels. And so within hydrogen, this is what it looks like. There aren't four of these. There isn't a yellow. I don't know why that's in there. And there's a teal, and then there's a purple. So it's not really good pictures in terms of colors. There's a red, there's a teal, there's a blue, and there's a purple. Okay, and they're missing that. But basically the idea is these drops down to energy level 2 are visible light. The ones that drop down only to energy level 3, they don't drop as far. Okay, energy level 3 is further from the nucleus, so they fall under infrared. Okay, a little bit less energy. The ones that drop all the way down to energy level 1, all the way to the ground state, are in ultraviolet. Okay, a little bit higher energy. So now, here's where it gets strange. We don't notice that those electrons, we don't see them in the middle of the elevator. There's no evidence that the electron is in the middle. There's no evidence of that as it makes that transition. And so as a result, we kind of almost have to say that it starts here and then it ends up there. Oops, ends up in the third energy level. Or it starts in the third energy level and it just spontaneously reappears in the first energy level. We don't actually see that transition. And you can't do that. I mean, if you think about it with matter, you have to make the transition. Mass can't just disappear and then reappear. It's not like you can go from the third floor to the first floor without making that transition if you are matter. But when it comes to electrons, we're going to treat electrons like waves, and waves can do that. It's just changing their frequencies. That's all they're doing. And if you consider like a radio station, all you have to do is turn the dial to change the frequency. Here with an electron, literally all it does is it's changing its dial itself. Okay? And as a result, we're treating electrons like a wave because of this transition, but we're also treating them like a particle because it has mass. We know what the mass is. And so it's very, very theoretically hard to understand. Okay, it's referred to as the wave-particle nature of light, or the dual nature of light, meaning waves behave as light, or light behaves as a wave, but light also behaves as a stream of what's called photons. They have mass. not very high mass, really, really low mass. And it's really complicated, but it's referred to as quantum mechanics. And we could go through and do the mathematics with you, but it would just absolutely lose you. So for basically what we're going to say is electron is a tiny, negatively charged particle that behaves like a wave in certain instances. So it does both. And light is a wave that sometimes behaves like a particle. And so it's kind of, that's basically what you want to take away from it. Okay, so atoms emit electromagnetic radiation. We're going to call that light. When the electrons in the atom drop from the excited state to a lower energy state, usually the ground state, because that's the lowest energy, that electromagnetic radiation, the light, is going to be emitted in what's referred to as quanta. They're discrete chunks of energy, okay, and they're only allowed to have certain values. And the farther away the electron moves from the nucleus, the greater the energy of that electromagnetic radiation, that light, becomes. Okay, that's the big idea. And as this progresses, electrons can be both waves and particles. It's kind of a weird concept. Okay, photons can also be described as waves or particles, except they actually do have mass, but it's really, 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 really small. So that's referred to as the wave mechanical model or the dual nature of matter. The big topic is referred to as quantum mechanics. We don't expect you guys to do a lot with that. Just kind of to know, that the Bohr model is not the end of the models of the atom. Okay, it's continuing to be developed. I mean, if you've heard about quarks, quarks are one of the newer discoveries of atomic modeling, and it's continuing to be developed as we have better and better ways of developing scientific data. So anyhow, that should hopefully help you with the lab that we're going to do in class.